Hello, I would like to present to you the outstanding coke suppressing and sintering preventive properties of platinum-4 germanium clusters on alumina support. My name is Guanjing Li, currently working under Professor Scott Anderson's group at the University of Utah. For hypersonic aircraft flying at 5 Mach and above, an effective heat sink is required from the fuel to maintain the craft's normal operation. One way to achieve this is to use endothermic reactions of jet fuels, such as cracking or dehydrogenation via platinum catalysts. However, conventional platinum nanocatalysts bear a few crucial disadvantages. For example, the catalysts are unstable, as high temperature reactions will cause sintering. Another problem is coking, where alkane dehydrogenation will deposit carbon over injectors and small channels inside the aircraft, causing unwanted issues. Regeneration via reduction methods, commonly used in industry, is not practical, as this also involves high temperature reactions which will lead to sintering. Our goal is to create a bimetallic platinum model catalyst that prevents sintering and coking. The catalysts are studied at a fundamental and simplified level, where we use flat alumina supports to hold bimetallic clusters in an ultra-high vacuum environment. Our focus is on small molecules like ethane. For endothermic cooling purposes, we want our catalyst to achieve a first dehydrogenation of ethane to form ethylene. After the first dehydrogenation, if ethylene binds to the catalyst in a strong di-sigma manner, ethylene will continue to dehydrogenate, forming coke precursors. We would like to avoid this from happening. Instead, what we want to achieve is a weak pi interaction between the ethylene and the catalyst. This weak binding will cause ethylene to dissolve off, thus preventing coke formation. We have simplified the experiment even further by assuming that the first dehydrogenation is easily achievable and only focus on whether ethylene dehydrogenates or dissolves from different catalysts after the first dehydrogenation. For analysis of catalyst properties, we dope germanium to the platinum and then perform temperature-programmed desorption that gives us information on binding site availability and catalyst reactivity. We also use X-ray photoelectron spectroscopy to find the atomic composition of the catalysts. And finally, we use helium-ion energy scattering spectroscopy to help us understand the surface morphology of the catalysts. Our work is about modifying platinum-germanium clusters. This is inspired by our collaborators' DFT simulations of platinum-germanium. They found that these clusters have higher sintering energies and lower ethylene desorption energies, meaning the platinum-germanium clusters are less likely to sinter and more likely to dissolve away ethylene than other candidates. The method of creating germanium-modified platinum clusters starts from using a beamline, where a platinum source is ablated by a laser source. The laser ablation creates a mixture of platinum ions that pass through a set of ion guides and a mass-selective quad via supersonic expansion to an alumina support in an ultra-high vacuum chamber for further in-situ analysis. The mass-selecting quadruples shown here specifically select clusters of 4 platinum atoms, as we found platinum-4 were highly effective in dehydrogenation reactivity. After platinum-4 clusters pass through the beamline, they are deposited to an alumina support until 0.1 monolayers of platinum atom coverage is achieved. Samples with only platinum-4 clusters deposited will be labeled as platinum-4 alumina in this presentation. 60 Langmuir of germanium chloride are then dosed to the platinum clusters, and then chlorine atoms are removed by dosing in 3000 Langmuir of hydrogen, followed by quickly heating the sample to 750 Kelvin. Samples with germanium-modified platinum-4 clusters will be labeled as platinum-4 germanium alumina in this presentation. After fabricating the platinum-4 germanium clusters, we need to know whether we actually incorporated the germanium to the platinum and not just germanium randomly deposited across the alumina surface without any association to platinum. This can be proved by XPS scans of the germanium 2p3/2 region on the surface of a control sample with only germanium dosed on an alumina support, compared to the XPS scans of the platinum-4 germanium. It is evident that we have more germanium on the platinum-germanium sample than on the germanium-covered sample. This indicates that the germanium selectively binds to the platinum and thus successfully creating platinum-4 germanium clusters. We can then record the platinum XPS intensities and the difference of the germanium XPS intensities, then taking into account of the photoemission cross-section, we can calculate the stoichiometry of the platinum germanium clusters, which happens to be around platinum-4 germanium 1. So 1 germanium atom in a cluster of 4 platinum atoms. The purpose of TPD experiments is to find whether dehydrogenation, in other words coking, occurs on platinum clusters but can be prevented when using platinum-germanium clusters. For platinum-4 clusters TPD experiments, we place a platinum-4 alumina sample in front of a mass spec and dosing 10 Langmuir of deuterated ethylene, C2D4, followed by quickly heating to 750 Kelvin while observing for the C2D4 desorption and the D2 desorption from dehydrogenation via the mass spectrometer. Then the sample is cooled down to 150 Kelvin and the TPD experiment is repeated for an additional 5 times, so a total of 6 TPDs are performed. The C2D4 desorption for the first TPD shows 2 peaks, a low temperature peak and a high temperature peak. This means that there are 2 kinds of binding sites for as-deposited platinum-4 clusters. The high temperature peak is associated with binding sites on top of the platinum clusters, while the low temperature peak is associated with alumina support, as can be seen for the desorption of C2D4 on a plain alumina sample here is also at the low temperature region. As for D2 desorption, we see a substantial amount of dehydrogenation, therefore indicating a large amount of coke formation. The coke formation is also reflected in the second TPD of ethylene desorption, where the high temperature peak decreased by 31% in intensity due to a mixed effect of both coke blocking off C2D4 binding sites on the platinum and that the platinum clusters sintered at the same time because of heating. D2 desorption also decreases for the second TPD as the sites for dehydrogenation had coked up or disappeared because of sintering. After 6 TPDs, the platinum-4 clusters are completely deactivated, with the high temperature peak in C2D4 desorption decreased to 66% of the first TPD. At the same time, dehydrogenation was minimal. The TPD experiment of platinum-4 alumina tells us the platinum-4 clusters are easily deactivated by coking and sintering. The same experiment was performed for platinum-4 germanium on alumina samples, and we see a drastic difference in C2D4 desorption and dehydrogenation properties. In the first TPD, the platinum-4 germanium clusters are still covered by hydrogen and chlorine atoms, so the C2D4 desorption and dehydrogenation was negligible. As for the second to sixth TPD, although there is an overall slight decrease of total C2D4 desorption due to germanium covering the platinum atoms' binding sites, the high temperature peaks are very similar in intensities and only decreased 18% after 6 TPDs. This indicates coking did not occur for platinum-germanium clusters, and the platinum-4 germanium clusters also have promising anti-sintering effects. Dehydrogenation was effectively suppressed in all TPDs, thus showing further evidence of coke-suppressing abilities of the platinum-4 germanium clusters. It is interesting to see a small but consistent amount of dehydrogenation that should lead to coking, but somehow the coke did not affect C2D4 desorption. We think this may be due to carbon atoms being incorporated into the platinum-germanium structure that still stabilize the clusters from sintering, while maintaining the number of sites for ethylene binding. ISS is a method where a helium ion beam is used to probe the topmost layer of samples. We collect a spectrum and normalize the platinum or germanium intensity by dividing it to the total amount of helium scattered signals. Multiple spectra are collected over a time period of 20 minutes, and normalized intensities are plotted as data points shown in this slide. Platinum ISS signals increase initially for as-deposited platinum-4 clusters due to adventitious adsorbates. The adsorbates are sputtered away by the helium beam, so more platinum atoms are exposed. The helium beam continues to sputter the sample and will start destroying the platinum atoms, which is why we see a decrease after further ISS exposure. Similarly, platinum-4 germanium clusters are covered by hydrogen and chlorine atoms, and then slowly removed by the beam sputtering, so the platinum signals increase with more ISS exposure. The 2 graphs in the middle display the ISS results after samples are heated to 750 Kelvin. Here, adventitious adsorbates are removed for the platinum clusters, while hydrogen and chlorine atoms are removed for the platinum-germanium clusters. These graphs are compared to the graphs to the right, where the platinum and germanium clusters go through one ethylene TPD experiment. The initial signals for platinum-4 clusters are lower than the initial signals of the post-750 Kelvin heat-treated samples, indicating coke formation on the platinum. Whereas the platinum-germanium clusters, after a single TPD experiment, did not show much change at all, thus indicating that coke was prevented. To sum up, we found the stoichiometry of platinum-germanium clusters to be platinum-4 germanium-1. TPD and ISS experiments show that platinum-4 clusters deactivate quickly from coking and sintering, while platinum-4 germanium clusters are highly resistant to coking and sintering. I would like to thank the hosts and organisers for this conference, as well as Professor Anderson for his advice throughout the last 4 years. Thank you.